Okay. Hello, good day to you. So today we're going to start following the tutorial that I shared last week. Yesterday. Yesterday was the first session. And the tutorial had a couple of assignments. We're going to go through one of the assignments together. And did we want to do some installations as well? So, okay, let me tell you, I have two things in mind. One is actually doing one assignment in Python inside Grasshopper. The other one is installing real Python with Conda inside VS Code. So we can do one first and the other one next. What do you think? Shall we do first the Python installation in Conda, or shall we first do the assignment in Python inside
I
Grasshopper?
prefer the assignment in Python.
In Python Grasshopper.
Please.
Okay. Okay, so let's get to it now. Let me share my screen. I just shared another set of lecture notes, but I didn't push it. I will push it now to the repository. Okay. And I'm going to go through it. It's basically the same content, but in a slightly better formatted context. So this is what we're going to do. Okay. We're going to make an object. In this case, it's a cone, because I want you to have a picture in mind as to what we're going to get out of this. So this is a picture of a cone that has been voxelated, and the voxels around the cone have been colored as to their distance to the cone. Okay. So this is what we're going to do, and this is what we're going to get. Something like this. Okay. Let me open the file that we had yesterday. Okay, so most probably we are not going to do anything with these, so I will just ignore these. And okay, we have a cone. Where's the cone? Okay, we have a cone, we have a bounding box. I showed you how you can get a bounding box yesterday, and I told you that the main library that we're going to use is going to be Rhino, and the geometry namespace within the Rhino common library as RG. Okay, just as a reminder, where is it? Let me close this.
Excuse me.
Yeah?
May I ask an elementary question?
Sure, all the time.
In your Grasshopper, there are some digits under the components. For example, 97 MS.
That's a
What are these?
profiler. Yeah, you want to get it? It's an interesting thing that shows you how long it takes for a component to do its job.
Oh.
And that is available. Where is it? I knew it. Document properties, was it here? Modify. Display. Yeah, display. So, where?
Preview settings?
No, canvas widget. Yeah, canvas widget profiler. That's the one.
Thank you.
A second, I'm going to close the door.
Thank you.
Okay. So, Rhino Common is the library, and let me open this one again. The library of code within Rhino. Rhino Common. Okay, this is old. Rhino Common API. Okay. Rhino.geometry. That's where we are, and this is what we are looking at. And what I used yesterday in the previous video was a method for finding the bounding box of a B-rep or a boundary representation. A boundary representation is a technical term for a solid that has been represented by its boundary. So if you want to represent a solid, you represent it with its boundary, and a boundary of a solid is some kind of a surface. So what you're looking at as a cone is basically two surfaces put together, one conic surface on the top and one circular surface at the bottom of the cone. So that's why it's called a boundary representation, or a B-rep in short. And so typically you have a type, a data type. In this case, it is a B-rep, or a boundary representation in short. And you have a bunch of so-called methods working on that data type. So these are all the methods that work on a boundary representation. Typically, if it is a geometric data type, you see a bunch of so-called constructors, which are the methods using which you can create an instance, a so-called instance of the object, or a copy of the template object. A type, a data type, is basically like a template. So you can use it to create objects of that kind, or of that type. And then the
For example,
properties, yeah, go ahead.
excuse me. For example, as the components of the solid, edges or surfaces or faces, and then we
Yes.
decide to which one to extract based on the data that we need. Yes.
Yeah, you can get the edges, the faces, the surfaces, etc. And these are the so-called properties. So you
Yes.
have constructors, properties, and other sorts of methods, right? So properties are the things that are somehow inside it, but some of them are also methods, right? So basically, when you ask
Yes.
this question, is it solid? Because you can have a boundary representation that is not solid, right? It can
Yes.
also be just a surface. The answer to this is a yes or no, or true or false, right? Is it
Yes.
valid? Does it have loops? If there are loops, give me the loops. If there are surfaces inside, give me the surfaces. If there are trims inside, give me the trims, and so on and so forth. Or give me the
Yes.
vertices, right? The
Yes.
vertices are the kind of points of the object, the edges, the faces, etc., etc. Or the curves, if there are curves contained within it. And the other sorts of methods, like adding a surface to it,
Yes.
etc. So everything that can work somehow with a B-rep or on a B-rep is somehow included here. Or for
Yes.
creating B-reps. So some constructors are somehow included like these. Create from a box, create from cone, create. So if I wanted to create the cone also by myself inside Python, I would have used this one, right?
Yes.
And you see
Okay.
this bool cap button. Bool here refers to Boolean.
Uh-huh.
Okay. So this is a
Yes.
Boolean parameter which says true or false. Do I cap the bottom or not? So you
Okay.
can guess that if I put a true, that means yes, I want the bottom to be capped, right?
Okay.
And if you
Yes.
say false, that means no, you don't want the bottom capped, so you just want the conic surface on the top.
Yes.
That's it. So you can pretty much guess what each of these methods do. And the basic rule remains this, that you always check the method here from the library if you want to know how to work with it, right? But after a while, you can also get used to this interface, and you can
Yes.
pretty much figure out your way by looking at the hints that it gives you here. Okay, so what did we want to do? We wanted to create a bunch of so-called voxels. Let me show you what we wanted to do. And then color these voxels with
Based on their distances from the center,
yes,
for example.
based on their distance to the surface. Okay. And so for the first steps, I would like to assume that the voxels are just single points inside as the center of the voxels, right? So we don't look at voxels as something more sophisticated. So for now, we look at them as a bunch of points, and for each of which we will have a box later on. But for now, just as points. Okay.
Okay.
So the
And
question
the
is how,
distance would be the shortest distance to the cone?
yes, which is shortest distance in this so-called Euclidean space
Yes.
is going to be the straight line distance to the
Oh.
cone. Okay.
Mhm.
But that's a good question, because for computing the distance of the objects to the cone, we probably need to find the closest point on the surface of the cone to that point. Okay. But let's
Yes.
do these things step by step. Okay. So first
Okay.
of all, we need to have the voxels, and then inside the box, and then we can compute their distances to the cone. So how do we create these voxels? How about first generating a grid of points on the ground, right? And then we will see how it works. For I in range of let's say 10, or j in range of 10. I'm just going to give it a try, okay? RG, which is Rhino geometry, point 3D. Let me put a size here. X size equal to 0.1, Y size equal to 0.2, Z size equal to 0.3. Okay. X size multiplied by I, Y size multiplied by J, 0. I want them on the ground. Okay, what's wrong with this piece of code? I can generate a point for every grid location, but I don't have any place to store the points, right? So I should first generate a list to store the points. So I generate an empty list called points. Points dot append. And it's a better idea to give it a name. Point equals this. Okay, let's see what we get. A equals points. Okay, not bad, huh? But so it's not that difficult to generate a grid of points. And as you can guess, we could have generated a 3D grid of points. How would that be? Just adding another loop
Z.
for k in range of
For range 10.
10. But then notice this, that the indentation defines the scope. So the indent of these two lines has to be increased as well.
By pressing tab?
Yes. Z size equals, no, sorry, Z size multiplied by K. Okay, not bad. Okay, but What's the problem? The problem is that this grid of points of voxels is not inside the box, right? So I should
Yes.
somehow obtain this from the box. So I have the box, I have the bounding box, right? And what do you
Yes.
think a bounding box is? A bounding box, I can tell you that it's not a very geometric object, it's just a bunch of numbers. So can you guess what these numbers are? Let's see what we have inside the bounding box, okay?
6 numbers of the points of the box.
Exactly. So this was not a very good idea. So let me give it another name, B. Okay, so that we keep the bounding box,
Mm-hmm.
and then let's see. Or actually, B sounds better for the bounding box.
Mm-hmm.
A equals points. Okay. Okay. So B box dot. Okay. Sometimes this little thing that we are looking for does not show up. It's called the IntelliSense, the intelligent feature. You know why it doesn't show? Because Python doesn't know that this is a bounding box. Let me see, rg.bbox. Bounding box. Let me see if this works. This trick,
You
no,
mean
doesn't work.
Python doesn't know all the Rhino commands?
No, the problem is that the output parameters of these cannot be assigned a type
Yes.
because they are outputs. For the inputs, you can assign a type um, and then you
Yes,
can
I
change
hear it.
them. Yes. What I can do is I can declare this bbox equals. No, that doesn't work. Okay, let's get used to it. It doesn't always show up here. But what can I do? I can go here and I can search a bounding box. Okay. And then I can figure out what is inside the bounding box. Okay.
Mm-hmm.
So basically what I'm looking for should be here in properties. Okay. So
Okay.
let's guess. I know what is the answer, but let us guess from the documentation uh which one of these properties is the one we're looking for. So this is gets an empty bounding box. This is not the one. Gets a bounding box that has unset coordinates, no. Area, no. Center, no. Diagonal. Yes, the diagonal vector of this bounding box. This one can actually do the job
Mhm. Yes, but
somehow.
it's rather
But
complicated.
yeah, this is only 3 numbers because this is a vector.
Yes.
Uh, is valid? No. Max sets the points at the maximal corner. Gets or sets the point in the minimal corner. These two apparently do the job because these two
Yes.
give us the two sets of 3 numbers. Okay. So let's
And
call
what
it.
about the volume?
Sorry.
And what about the volume? The last one.
Volume is just a number, so it doesn't do what we need.
Uh-huh, uh-huh.
Okay. So let's call it min corner equals bbox dot min max corner equals bbox dot max. And you know what? Let's print them to see what we got. Yes. Okay.
Mm-hmm.
Okay, so we have these two numbers. How do we generate the numbers that we need from these two numbers? So first of all, basically the diagonal will be helpful as well. Diagonal equals B box diagonal. I have a proposal. I would start from the B box minimum. No, wait a
Subtract.
second. And then use the diagonal entries. The diagonal entries we can definitely use for XS, YS, and ZS. But then we can divide them by some numbers. Or we can do it differently. We can start from
Subtracting the maximum, minimum from the maximum.
subtracting minimum from the maximum gives us the diagonal. What else can we do? We can generate some.
Do we have the height of the cone? Because we have the radius.
Yes.
If we have the
Well,
height of the cone.
well, we have everything inside the bounding box, right? So the
Yes.
minimum corner is a point with coordinates here. Maximum corner is a point here. So basically, this gives us 6 numbers, and the diagonal gives us 3 numbers, which shows the width, the length, and the height, right?
Yes.
So
we need to.
So there are 2 ways to define this. One way is to define a voxel by the number of voxels or the voxel based on the size of the voxel. Okay, so I would say a better way to deal with this is here. What did I do wrong? I know. Diagonal. You see, it doesn't have an object starting with a small case d. It has to be diagonal with a capital D. That's why it's complaining. Diagonal. Okay. Okay, so I think that the size of the voxel is a more important vector. So I'm going to give it a vector for the size of the voxel. I'm going to call it a vector 3D. And I'm going to create it like this. Okay. And basically here we can say that, yes, okay, this is a vector 3D. Okay, this is better now. So I would say xs is vs dot x divided by diagonal dot x. And this is something that I remember, but you can check it out. If it's a vector 3D, it has 3 properties, x, y, and z. Let me show you. See, vector 3D, properties, x, y, and z, all capital, right?
Yes.
And svec, actually, I wrote this wrongly. Actually, this has nothing to do with the diagonal, right? We want them to be
Yes.
of this size.
You are using the constructors,
Yes.
not the properties. Yes. Vector 3D, point 3D point.
No, no,
Yeah.
not the constructors, the properties, you see?
The properties. Um,
See? X, Y, and Z. So I'm just getting them because they're defined already.
yes.
Yeah.
Yes.
But the next thing that I'm going to find is the number of these repetitions. For the numbers, let me call them something nice. U count equals the diagonal count of the box divided by X size. V count, W count. This must be about Y. This must be about Y. This must be about Z. This must be about Z, right? And I'm going to replace these with U count, V count, W count. Okay. Okay, what's the problem? Range, integer, and argument. Okay, got float. Okay, because, of course, because they need to be rounded to the nearest integer. For that, I import math. Import math. And then I do math dot round. Is there something called round? You know, I can do this one first. I can convert them to an integer. Okay, so you see everything seems to be okay right now in terms
Yeah.
of the size, right? But the whole thing is shifted. Why? Because they're a bit off and we can do this. We can add the minimum corner to this point. And then they will be inside. Is that good?
Yes. How did you shift the starting point by the radius?
But sorry, what?
How much did you shift the starting point of the?
Oh, by the minimum corner of the bounding box, because that one has
Uh-huh.
negative coordinates and that one then
Yes.
pushes everything to the right location, right?
Okay.
And we shouldn't be so much bothered by these things that do not fit inside. If we don't like them to be so much on the edge, then maybe we can remove the ones that are really on the edge. How about that?
Yes. Good.
So, um, then let's define. I'm not so sure if it's necessary. Tol for tolerance equals some number 0.1, and let's say if point minus minimum corner that x larger than 12 and y larger than tolerance and z larger than tolerance, then because we have an if, this is a control flow mechanism, right? So it has to define a new scope. So therefore I
Yes.
have to put another tab to go this to take this further inside the
Yeah.
scope of if. And after this I have to have, okay, something got wrong here. Point 3D, line 27. Point minus minimum corner. Okay. Okay. Uh, Probably a better idea to put these inside parentheses because each of them is either a true or false. And so the problem is the following, that the point 3D in Rhino is 0.3 double, and doubles do not exist in Python. What exists in Python is floats, right? So this point is now a point 3D, which is now being compared to a float, which is wrong, okay? Because two data types have nothing to do with each other. The point dot x should be compared, and the point dot y, and the point dot z. Now you see everything is working. Yeah?
Yes.
Do you see what the problem was?
Yes.
A point 3D is a compound data type that cannot be compared with a single number. Only things of the same nature can be compared. Okay?
Yes.
So
Yes.
I was hoping to achieve something that was actually impossible. Okay?
Okay.
So now I have the voxels. So far, so good. They look pretty nice. Okay. Now I want to measure the
And their size is
distance.
only 1 point.
Sorry.
And their size is only 1 point.
Their size is determined here as a little box.
Ah, yes. Okay.
So we can do two things. We can first color them, and then we can create the boxes around them, or we can first find the distance and color. Or first we can create the boxes and then color them. But I think it's easier if we first color them according to their distance. Okay, so let's create a list of distances as well. It's an empty list again. Okay. So where should be the scope for adding the distance? It should be the same, exactly the same as this is scope, because we only accept a point to be a voxel if it's here, right?
Yes.
So
After passing the
here,
tolerance.
yes, if it meets the tolerance condition that we have defined.
Yes.
So let's define something else. Okay, let's do the following. The brep object that we have, how is it called? It is called solid, right? Solid. So solid closest point to this point. We call it CP, closest point. Right? That
Okay.
will be the closest point on the surface of the cone to our point. And then distance will be CP dot distance to, and I know this by heart, but you can check it
I'm checking.
from. Can we check it? Let me see. Point 3D. Point 3D constructors, no. Distance 2. Yes, distance 2. That's the method, and we had a boundary representation, brep, and I was looking at a method for finding
This one.
closest point. C, closest point. Yeah, finds a point on the brep that is closest to the test point. Exactly. Okay.
Okay.
And so this is the distance, and distances dot append distance. Very good. D distances. Okay, let's see what we get here. Okay, this looks reasonable. So, there's something else a little bit more interesting that we can do to make the so-called sign distance. So if they're inside, because we have voxels inside and outside the cone, if they're
Yeah.
inside, we can make them negative distance, and if they're outside, we can make them positive distance. This is called a sign distance. Okay,
Okay.
let me see if this cone actually has a cap or not. Does it?
There's not.
It doesn't. Okay. Cones. It's not very important, but okay.
No, it has.
With a zoom selected, Z space S space, I zoom onto the object very quickly to see what I get. And this is the meaning of a boundary representation. You see, it's consisted of two surfaces, which together
Yes.
form the boundary of the object. And this one is a single NURB surface. I don't know if you see this, but this one is a little bit thicker than the other three lines, because it's the line where the two
Yes.
ends of the rectangular surface patch meet each other. And this one is
Yes.
also cut from a rectangular surface. You see this cross here on the surface, and this is actually a trimmed surface. If I press here on trim, I can select an edge and untrim the object. And I can get the original surface from which it is cut.
Yes.
So this was just to show you what this actually is. Okay.
It's because the constructors of the base surface is basically a rectangular. Yes.
Yes, exactly. NURB surfaces are rectangular by nature.
Mhm.
And you might just wonder what on earth that could mean for some surface like this. I just left out one thing. So both of these surfaces I said are rectangular, right? We
Yes.
just saw how rectangular this one is because it is trimmed. And I
Yeah.
said this one is also rectangular, but it doesn't look like a rectangular surface. That's because one of the edges has reduced to 0 here.
It's trimmed and then bent. Yes.
Yeah, it is bent, but one of the edges of the rectangle,
It's
so this is
doubled.
one edge, two
Yes.
edge, three edges, and the fourth edge has reduced to 0. But you can think of it as a very, very tiny little ring here.
Yes.
That edge also exists. And I can show it to you as a subsurface. It's called subsurface. Anyway, I've forgotten this. You know what I mean.
Yeah.
Domain. And look it up from here. Network, exclude, surface from points, analysis. Let me see. What is it called? Is that a new stuff? Isotrim, yes. Okay. So if I explode this first, for BREP components, get the BREP components. The names of some things have changed. Nope. Let me get it from here. This is surface, domain, construct the domain, two-dimensional, domain, domain, zero, one. Not good. Okay. I reparameterize it and okay. Now I have it. move it somewhere else so we can see it. See?
Yes.
So if I start from something other than 0, you see how this actually approaches to a small, very small ring.
Yes.
But you see that the whole thing is rectangular by its nature.
Yes.
Yeah?
Yeah. Interesting.
So this is what we are dealing with. Okay, we can
Okay.
do everything that we did here, we can also do it inside Python. So actually it's a good idea for you to try this later.
Okay.
Okay, so where were we? Okay, so I just wanted to check if it is inside or not, and if it is inside, I want to change the distance to negative distance, right? So let's
Yes.
check if there is a method called isInside. So I just use Control F, inside, is point inside, okay? That's exactly what we need. And let's check tolerance strictly in. Okay, sure. Okay. So exactly here, right? Or after the distance is computed. If, and how do I know that this one actually gives me a Boolean? Because when you look at it, determines if the point is inside. I can actually open it in another page. You can see here that it says it's a Boolean function. So what it returns is going to be a Boolean, right? And
Yes.
3 arguments are needed. The point that we want to test, a double precision
Tolerance.
floating point, which is a float in Python,
Mm-hmm.
a Boolean to say whether we want it to be strictly inside or not. That's it. And it returns a true or false whether or not it is inside. Okay?
Yes.
So CP is the point, tolerance is tall, and true. Right? Because I just remember. And what do we need to do with this? We need to increase the scope, the depth of the scope. As negative. And if not, we need to decrease the scope. Well, basically, let's do it this way. Distance equals negative distance, right? And distance says that append distance. This is cleaner, right? So only if it is inside, then we change the sign of distance to negative. And then in either case, it is either changed or not. Distance is added to the list of distances. Okay?
Okay.
But we have an error, so this point inside. Ah, of course. What do you think is the problem? We didn't say is point inside what?
We didn't select the BREP.
Yes, exactly. Okay, so now I expect some of these to be negative. Oh, that's disappointing. None of them is negative. Why?
Because none of them is Oh, yes.
How is that possible? How is that possible? Maybe it's a closed VRF and this one is an untrimmed surface. Okay, so this one seems okay. This one
I
seems
think the
okay.
BREF should be a closed surface.
It is closed, yeah.
Even in the, it is,
Mm-hmm.
but it doesn't have a bottom surface.
It doesn't have volume?
No, it doesn't have a bottom surface.
Oh, it didn't have a bottom surface, but I added a cap to it.
Oh, yes, yes.
And after this operation, it is a capped or closed surface or closed BREF, basically a solid.
Yes.
So let me
Is
see.
it possible that they are two separate surfaces?
I don't think so, because it says it's a closed surface. So basically, okay, let's check this out here. Print solid is
Closed.
is solid. Hmm? True. See?
Yes.
And let's get its volume. Does it have something to compute volume?
These are the list that you are searching through is the functions
BREP.
of the Python.
Yeah, methods. Methods from Rhino Common. They have nothing to do with Python. They're coming from Rhino Common because solid is a boundary
This
representation.
this list is the
Yes,
Rhino command.
yes. This is exactly the same. So any one of them that you see with this little icon is basically a property, and the ones with the pinkish boxy icon is a method.
Method. And what about the constructors?
Constructors are also methods, so they have the same icon.
Mhm.
So basically, you only see these two icons in most cases.
Mhm.
So let me see. Let us check here if there's something for finding the volume. Get volume. Okay. Get volume. And okay, one important thing about methods is that methods always end with parentheses, even if they don't have arguments. You see? It even
Yes.
has a volume. Okay. Uh, so let me check one thing here. Shouldn't make a difference. Okay, let's do something and we'll get back to this. But in the meantime, you can think about why this is not happening. I'm going to use these numbers and their range.
Color.
So I'm going to first find their bounds or the range of these numbers, and then deconstruct this domain. You don't have to know all these tricks in Grasshopper. I'm eventually going to use only Python to do this. And I'm going to remap them to the range of 0 to 1. This is a source domain, and the target domain is going to be 0 to 1, and then I'm going to use this one, and let me see. Okay. Dot display. These colors, I want to present these points with these colors and show me these points. Okay, not bad, huh?
Yes.
They're very huge. So, and maybe I can turn this off. Not bad. Apart from the fact that we haven't yet managed to okay, so you see when they're close, they have a color, reddish color. When they're far, they have a bluish color. Okay.
Okay.
But we actually wanted the ones inside to have a different color, but maybe this is not something so interesting for now. I mean, we will eventually solve it, but let's do something more interesting. Shall we produce these numbers like these remapped numbers inside to give it to the preset colors? Yeah,
Remap
instead
the
of doing this
numbers.
operation, yeah, remapping the
Yes.
numbers, instead of this operation, we do the whole thing in Python. Yeah.
Yes.
So for that, okay, basic question. Do you think I should do it inside the same loop or should I make a new loop?
Maybe it's better to make a new loop
Why?
because you've already get the points,
Mm-hmm.
and then you can start a whole new process on them.
Yes, the important reason is that we need to know what is the maximum number that we have in our list. And before the list is completely made and finished, we cannot know what's the maximum. So it's better to
But
start
the
a
list
new
is
loop.
complete.
Yeah, but after the list is completed, then we can find the maximum. So we have to do this in another for loop. Okay.
Okay.
So normally I don't do this inside Python and I don't do this with for loops because this takes a long time, but this is educational, so let's do it. So for distance in distances, I'm working so much with NumPy that I don't remember how to do this in Python. We have to find the maximum, find the minimum, and then do it. Well, actually, it gets more complicated than I thought. Let me see. Of course, we can do it, but it's not very smart to do it this way. Does it have a maximum function? Python, how to find value in a list. List max method. Okay, it does have function. That's easy. So print max of distances. Pretty good. Okay. And
So
so we have max and min. max d equals max distances, min d equals min distances, and okay, what's the remapping operation? So for distance, okay, let's create remapped d equals an empty list for distance in distances, right?
Yes.
Remap d equals distance minus min distance divided by max d minus min d. Correct? Something like this should do the job, right?
Yes.
Remap
This
distance.
menu.
Okay. And let me put it out. Did we do it? Yes, properly. Is that good?
Yes.
Okay, so we get rid of these. And we can also generate colors directly in Python.
I have a question.
Yeah.
You were coding inside this Python component in Grasshopper all the way.
Mm-hmm.
Yes. And but before this last step, I asked, and you told me that you're using all the Rhino commands.
Mm-hmm.
And how did you switch to Python in the same space?
Well, this one is basically Iron Python. So it looks
Yeah.
like Python exactly, but it
Yes.
can also communicate to a library that is written for .NET languages or something like Rhino common. So
Okay.
inside this component, you can write Python and you can access geometric operations from Rhino common. That's not a problem.
Uh-huh.
The problem appears when you try to import libraries from Python that cannot be imported here. So
Uh-huh.
libraries like NumPy, SciPy, they cannot be imported here. The new libraries of Python cannot be imported here. So only some very basic libraries can be imported here.
Mm-hmm.
Okay. So that's
Okay.
the only problem. So basically what you are learning today is not really about Python, it's mostly about Rhino common.
Okay.
Of course, we are writing everything in the syntax of Python,
Yes.
but we should be aware that this is not real Python. This just looks like Python.
Yes.
Yeah.
Yeah.
The problem is that if we believe that this is Python, then we should be able to import real Python libraries, but we cannot do that here. So
Yes.
because it's not real Python, it's Iron Python. IronPython is a language that looks like Python, but it's written to communicate with .NET libraries, like libraries that have been written for C# and Visual Basic. And that is the problem, because Rhino Common has been initially written in Visual Basic and C#. It has been rewritten for C#. And it's not written to be used in Python. You see?
Yes.
That's the issue. But okay, for now, we want to get started from somewhere. So this is where we started. So far so good, but let's do something else, some other geometric thing. I think it would be interesting to do one more geometric thing to make something interesting. The other thing that I want to do, I can do it inside another component, but yeah, maybe it's cleaner if I first do it inside another component and then I bring it here. It is from one of the slides that I've put here. So basically we did this so far. For each voxel center point, which we
Yes.
generated,
Yes.
find the distance to the brep. If the voxel point is inside the brep, mark the distance as positive. Otherwise, mark the distance as negative.
And it's
We
called
did,
pseudocode because it
yes,
wasn't
yeah,
originally in
yeah.
Python.
Because this is
Okay.
not a code that you can write in any language, but this is written for a human being to understand what the algorithm is about. Basically, when I'm thinking about an algorithm, I write something like this on paper.
Oh, yes.
Because
Okay.
in my mind, I can imagine how this can possibly work, right? But then, of course, I remove all kinds of small details that are specific to a single programming language
Yeah.
to make it human readable. So this more or less looks like a poem, doesn't look like an algorithm. Well,
Something like
so
the wireframe for the.
yeah, exactly. Okay, so this is the next thing that I'm going to do. I'm going to generate a little box, little thing for every one of those voxels as a mesh.
Yes.
And for doing this, I'm going to use a method from Rhino geometry mesh objects, which is called mesh create from box. Okay.
Yes.
It is very important to use
The
um,
problem.
the proper ordering of the vertices of the mesh to get the mesh right. Can you imagine why? That's because of the orientation of the faces of the mesh. So we need to know in which order it needs this enumerable or list of points to be fed into it. Okay.
Okay.
So I hope. But okay, let's find this method on the documentation. Mesh create from box. Okay, keep that in mind.
Okay. Mesh from box.
Mesh create from. Okay, let's first go to meshes. Mesh. Okay. Mesh from create from box, right?
Yes.
Create from box with an enumerable of 0.3D corners. Okay.
Okay.
Okay, perfect. So this is the method, and you see a little thing called static here. This is a very important point. So let's read this together. Static
The
mesh
static.
create from
Yes.
box, bounding box, integer, x count, integer, y count, integer, z count. So what do each of these things mean? So this one you know already. This one determines the data type of the output of the function.
Yes.
correct? Because this is the keyword that comes right before the name of the function. Okay,
Yes, like Boolean.
exactly. So this
Okay.
tells us that the output of the function is going to be a mesh. Okay,
Okay.
this one tells us that the first argument of the function has to be a bounding box. This one tells us that the second argument of the function has to be an integer. The third one has to be an integer. The fourth one has to be an integer. Right?
Okay. Yes.
But what on earth does this one mean? This one means that it's not a dynamic method. Dynamic methods are not written as dynamic blah, blah, blah. They're just written as methods. But basically, all other methods that we have seen so far have been dynamic methods, meaning that they can be run on top of an existing instance of an object. It's quite a mouthful. Let me repeat. An object is like a data type, okay? So
Okay.
when I tell you that we are talking about circles, that means we are talking about the data type of circles. Am I talking about a particular circle? Not yet. I'm talking about circles in general, right? So
Okay.
an instance of a circle is an instance of an object called circle, right?
Yes.
So an instance of the type circle is a particular circle. It's an instance of the type circle, right?
Yes. Yes.
An instance of the mesh object is a particular instance of the mesh object, and we can call it a mesh, right?
Yes. Yes.
Most other methods that do not have this keyword static behind them are so-called dynamic methods. That means that they can only be run on top of an existing instance of an object. What does that mean? Practically, that means that you need to have a mesh to run a method that is called, for instance, uh,
Okay.
that is called, let me see, base normals, for instance. You see, it doesn't say anything here. This is the data type, mesh face normal list. It's quite a mouthful, but it is a single word. So this whole thing is the name of the type of the output of this function. This is a property, actually. Let me get a function. It's better.
Method or function? Method.
I need a method. Closest mesh point. Okay, closest point.
Yes.
Let me show this one. Okay, this is going to return an integer. Why, that's another story, but because this is going to return the integer, the face index of the face of the mesh that contains the closest point, but that's another story. But what we see from an object-oriented point of view is that it's going to return an integer. This is the name, but it doesn't say static. So that means it's a dynamic method. What does that mean? That means you need to have a mesh instance already to be able to run this on top of it. Do you see what I mean? There has to be a
Yes. Yes.
mesh on top of which you say, let's call it this mesh, right? So this
Yes.
mesh dot closest point you have to run, right?
Yes. Yes.
But when it says static behind the name of a function, that means you don't need to have an instance. You can just say mesh in general dot create from box. You don't have to say this mesh.
It means that it has a mesh inside this function.
No, it is a general method that doesn't need an existing object of that kind to operate. Because
Okay.
as you can see, this is going to create an object from scratch,
Yes. Yes. Yes.
right?
Yes.
So that was just to explain what this word static means. So most of the methods that are object constructors actually start with this term because they don't need something existing to start. Okay.
Okay.
Okay. So where were we? Okay. So I will first do it inside another GS Python component. And for now, I define it as a single point 3D. I don't define it as a list of point 3D, and I will tell you something very, very important about this later on. I will connect it to this one. And svec, exactly this size vector, because this size is basically the size of a single voxel, right? And
Okay.
P is a single point. Okay. So we have a point 3D. I pretend that I have a point 3D, a single point 3D. I don't bother so much with the fact that it's actually a list of points. And before I forget, that's because Grasshopper automatically iterates with a for loop through them. And that's something that confuses people because they don't expect it to do this, but it does. Because Grasshopper is designed to make people happy. So it automatically iterates through the list. But when we do it in code, we have to do it explicitly. So let's work on this. Okay, so where was it? Here. They have to have this particular order. To create this particular order, I'm generating some vectors from the center point to create these 8 vertices, as you can see here.
Yes.
And then I create some mesh faces. The mesh faces are basically telling us how each face is wound around the center of each face. And I'm trying to keep a consistent orientation for all the faces. So if you think about it, I'm trying to make a right-hand orientation so that when I wrap around a face, for instance, 0, 4, 7, 3, when I
Yes.
wrap my fingers in my right hand around 0, 4, 7, 3, my thumb will be pointing leftward.
Yes.
That's an outward orientation for a mesh face. Now look at another one, 0, 1, 5, 4. If you do this, your thumb and your right hand will be facing towards you,
Yes.
right?
Yes.
And if you notice, all of these mesh faces have been written carefully exactly in this way.
Yes.
So 0, let's check another one. 1, 2, 6, 5. You see? 1, 2, 6, 5 gives you an orientation rightward.
1, 2,
And
6, 5. Yes.
2, 3, 7, 6
6.
outward orientation again, which is backward right now. And 0, 3, 2, 1, which is downward, which is also outward for the box. Because we want all the faces to face outward, right?
Okay.
This is about the mesh faces as in this, and these particular coordinates are about the coordinates of the vertices. To get them exactly in this order, 0, 1, 2, 3, 4, 5, 6, 7. Okay.
Okay.
So, but this code is written in C#, so I have to write it in Python. It will be slightly different, but the same kind of logic applies. This shape, okay, let's see if I can copy this shape from the documentation. Yes, they have it here. This is a shape that is written in ASCII characters. This is a very nice habit by programmers. Sometimes they write shapes by using ASCII characters, which are the characters that are available on every single keyboard. Right?
Yes.
So you can copy
Yes.
this and you can actually bring it to your code for a little help. but it has to be marked as multi-lines of comments, and I haven't yet talked about comments in Python code. Basically, if I put 3 of these little characters here, I don't know how to call them. You know where they are? You know what is the tilde character in your keyboard?
Yes.
So the same key usually also has this little thing that looks like a quotation mark. Did you find it?
Yes.
Do you know how it is called in English? Did I do this right? Actually, let me
Tito
see.
mark. Tito mark.
Ditto.
Yeah. Is it like the double quotation mark? It's like the quotation mark?
Like a single quotation mark. But actually, I
Single.
got it wrong. I should have used a single quotation mark instead.
Single. Apostrophe prime. No. Apostrophe.
Yeah.
Yes.
Yeah, the previous character was wrong, actually. We need to use a simple apostrophe. Yes. Or a single quotation mark, yeah. 3 of them for beginning and the end of multi-lines of comments, right? Okay, so I'm going to do it here, and when I think I'm done with it, I will wrap a function out of it and I will bring it as a function over there. Okay?
Okay.
But let's first do a simple test of function making here, because this is something nice that can be also wrapped into a function. Don't you think? This little thing. This was a function that is likely to be reusable. So let's call it def
Yes.
remap numbers and num oops wait nums or num in nums remapped in num max number min number nums num in nums, where is it? Remapped number this is how you write a function. It has to have something to return, right?
Mm-hmm.
If you're not sure what to write in the function, the first thing you write is a pass, so it doesn't give you errors, so you can write.
Okay.
Maybe it's a good idea to write
Then
a
you
single
will.
line of comment to say what it does. Maps
It's like a note.
Yes, exactly. Okay,
Okay.
so I remove this. This is a single line that explains what this function does, but this does not execute because I've commented it out. And basically, I think I have everything here. So let's give it a try. Instead of this, I want to use remap numbers, distances. Oops. Expected an indented block. Where? On line 48. Ah, of course. You see that the error actually tells us exactly what we need to hear. It expected an indented block of code, but we didn't give it an indented block. You see the
Indentation is,
problem?
yes. The
These
indentation is,
two have to
yes.
be like this.
The scope was wrong.
Yes. And something went wrong. Something went wrong. I leave it for you to figure out what went wrong because we want to go forward. So for now, I use map distances. Okay. And get back
Okay.
to this business. Okay, where were we? We wanted to create vertices equals a list.
And this shape acts like a geometric node that we use
Yes,
to
yes,
remember the place of the vertices. Mm.
yes. So for basically a for loop doesn't help that much because we need to create exactly 8 vertices and exactly 6 faces. Okay. So
Okay.
imagine a center point here,
Yes.
and let's make a new vector called, let's create 3 numbers called u equals size svec that x divided by 2, v equals s, what's the name? Yeah, svec that y divided by 2, and w equals svec that z divided by 2. Okay,
Okay.
and v0 equals
That's like
p plus rg dot vector 3d. Okay, so tell me, negative u because we have to go left, negative v because we have to go down, and negative w. Negative u, negative v, negative w, right? And this is going to be v0, v1, should be plus u, but everything else should be negative. 2 will be plus u plus v, right?
بله.
3 should be plus v, but minus u. That is 3. 3, 4. 4 is minus u minus v plus w plus u minus v. Oops, 5. 6 is plus u plus v, everything plus. And then plus minus u minus v plus, no, minus u plus v.
V plus Z
Yes,
plus W. Yes.
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 Okay, so vertices equals, basically I can declare them here, equals v0, v1, v2,
V
v3, 4, v5, v6, v7, all of them. Okay, now f0 equals, okay, let's create a new mesh rg. Okay, wait, box equals rg dot mesh dot create from box. You see, this is exactly the method that we were looking at. Vertices 1, 1, 1. B7 is not defined. Okay. Forgot to.
Okay.
You see, we got all of the boxes now.
Yes.
Basically, we didn't have to define the faces because this method takes care of it directly inside. So all we had to do was to generate the faces in that order. And you see that the iteration is happening automatically.
Yeah.
That's because Grasshopper takes care of it. But in future, we won't rely on this.
Why?
Because we want to do it explicitly. To see exactly what's happening. So these are our little voxels. Very
Okay.
nice and beautiful. Okay.
Okay.
So
And it made all the voxels, not, for
yes,
example,
all of
just the
them.
red ones.
Yeah.
We can.
But you see, we actually had to iterate through them. but we didn't
Yes.
iterate. The iteration is happening automatically by means of Grasshopper. And it's creating a data tree out of them. No, a list. But it's doing it automatically. So now I'm going to make a copy of this and make a function out of this. And then I will bring the function inside the other one.
Okay.
Okay, so how do I generate the function here? I define def box from
Yes.
voxel voxel
Voxel, voxel.
voxel a voxel. That's just the name that I'm giving to it. Point or voxel point voxel size. Okay. I change this name to voxel size, right?
Okay.
And then I bring these stuff. Yes.
Yes.
And vertices equals and then return box. Is that good?
Yes.
So
When
this
you're
is
defining when you're defining something, what does the point do? For example, SVEC point z divided by 2. What does
a
it mean?
dot. The
Yes.
dot. The dot accesses a property or a method. So x is a property. So
Yes.
by dots, we basically go into the list of properties that are available on the box. So when I press the dot, basically I see all of the things that are available on an object.
Okay.
Do you remember? So the vector 3D, for instance, it has a property x, y, z, right? After I put the
Yes.
dot, I can access x, y, z, or I can access any of these methods. Yeah.
Yes.
Okay. So instead of doing it step by step, this time I want to call the method. So I call it for this point and svec. And as you can see, these names don't have to be the same as these names because it just expects.
I lost your voice.
Okay. No, they're all here.
Okay.
Okay, so everything is here. Okay. So I'm ready to bring this function into the other one. Okay. Well, actually, because I want to call it, I have to bring it on top of this. Because I want to call it afterwards.
Yes.
And I'm going to define a list of boxes. And I'm going to add boxes that append box. And I'm going to make a box and call it voxel voxel point svec. What is it? Runtime error global p is not defined. Where is it? Ah, p. There's no p. See?
It's a little bit hard for me to read,
To
but
understand
it's very
what
short.
went wrong.
No, no,
I
no.
still had it for with p, okay,
Yes.
and that was not acceptable because here
There's
in
no
this
P. Yes.
context, in the scope of this function, it it doesn't know what this is, but here it had it from the memory, so it worked. Unfortunately, it gave us the wrong impression. But actually, it should be only using the things that are inside the scope of this function.
Yes.
So P doesn't exist. So P was actually this input.
Voxel point.
Exactly. So sometimes an error represents something much bigger and we have to correct it. Okay, so now we have the boxes as well. And let's say B equals to boxes. How about that? And we get B for boxes. We have them. But basically, instead of a box, we should call them meshes. Okay?
Okay.
But I want to color them also. Should I color them or should we call it a day and color them afterwards? Because that takes a long time. It may be enough for now.
Okay. As you prefer.
I think maybe we can call it a day for now
Okay.
and think about how to color how to color the meshes properly until tomorrow.
Where can I find the functions, how to write the functions of the Python?
So good question. So let's search Python, how to write function. A good library, a good tutorial like this. But as you can see, again, this is not so much about Python. This is actually about geometry
Yes.
and Rhino comments, right? But the basic
Okay.
stuff are here. And there's a very good tutorial, learn X in Y minutes. Or Python. This is the shortest tutorial that I recommend to people if they want to learn Python quickly. If you follow this, then you're basically good to go with Python itself. And if you want to run it, you can run it inside your VS Code or inside even some online editors allow you to code. Maybe it's easier if you write it inside your VS Code.
Okay.
Yeah.
Yes.
Shall I show you how to do it in VS Code?
No, I can search for it.
I can also show you,
Okay.
but maybe not in the video. Okay.
Okay.
So let's stop this for now. We'll only save it to the repository. Import as this one, replace it, yes.
And also as a grasshopper file.
Save.
Document.
This one is directly saved here.
Yes.
Okay. And then I have to commit these.
And then push.
Yeah. There you go. Great. Your little icon has appeared here. Very good. So good.
Yes.
Okay, so far so good. Let's stop for now.